So my talk has a very long title, and yet it conveys surprisingly little. So it actually looked somehow smaller when I was drafting it, but anyway, so what we're going to talk about. We're going to talk about WebAssembly and its system interface, which we're going to explain in a short time. But we are going to explore those topics from the perspective of a system engineer. So we're going to be in the position of people writing system software and daemons, stuff running in the back end, and with some emphasis on also on the cloud infrastructure, meaning the software components which actually enable the container to run. Kubelet, think about runc, if you know it, Cryo, and containerd, and the likings. And from that perspective, we are going to explore what WebAssembly could bring us for us to the table. So we are not starting from like the web environment and exploring what WebAssembly system interface is, but rather from the other angle. We are backend people trying to writing system software. So is WebAssembly good for us? What could give us? Now, WebAssembly. And it's a system interface. So the system interface is one way to run WebAssembly outside the browser with having access to an API, which is a subset of POSIX, so you get network access, file access, and the likings. And according to survey in the WebAssembly community, this usage as extension, like running WebAssembly as plugins, is actually something that people are looking at. So our exploration is not, like the weekend hack, is something that other people well around are also trying to do. So looks promising so far. So before we start, who am I? I'm a software engineer working at Red Hat. I work in the Kubernetes area, namely in the node area. So I contribute to the kubelet, I contribute to the container runtime. If you are interested in running containers at low level, if you're interested in low latency software, you're interested in making those containers run fast and have access to hardware, come talk with me. But this is, my own journey, so mistakes are my own. Now, the talk is divided in 3 main sections. I was told to go fast and go quick, so we're gonna have a very quick introduction about what is WebAssembly in Go, because again, we are starting from the Go engineer perspective. We're going to see how does it look like to try to extend our software using WebAssembly runtime and to enable WebAssembly plugins, and how the people which actually are building cloud orchestrator like Kubernetes or the tools which power the container runtime, how they are trying to use WebAssembly. The QR codes you see, if you scan them, they will point you to the GitHub repos on which I have all the examples on the code I'm showing. It's much, much more. Now we're going to be really fast and really quick, but all the examples are there. So the first section is what we can do with Go. 1 out of 3. Okay, so in Go 121, very recent, the latest stable release, we got official support for WebAssembly system interface. So once again, you got WebAssembly, which is a compilation target. It's a binary format, much like ELF or whatever. But that binary code was meant to run in the browser at the beginning. And now people were start to looking, okay, can I run it outside the browser? What I can do with that? And the system interface, WebAssembly system interface, is a way to run that outside the browser. So standalone, kind of like. It's not the only way, but it's the way which is gaining more traction. And from Go perspective, nothing surprisingly, you set Go operating system, you set a Go Arch, and you can cross-compile like you would do, for example, from Linux to Windows or whatever. And what you get, it's this binary format, which you cannot yet, maybe, but you cannot run natively. So you need a runtime environment for that. One thing which I like to point out is that you set to Go Arch. So if you're trying to do system software and you have Linux-specific build tags, maybe worth having a closer look before to just jump on it. So we have a binary format. We need a runtime to run it. And the one I want to highlight, because I'm simplifying a bit more, is the WASI runtime, which is written in pure Go. So it's very, very, very easy to implement and extend our own Go application using that. The only thing I want to stress is that there are many, many others. So the runtime works very like a virtual machine in the sense that it's a sandboxed environment on which our WebAssembly code runs. If there are WebAssembly in the crowd, I'm overtly simplifying because I'm coming from the Go angle. So the one noteworthy thing to know is that if we run our WebAssembly payload inside a container, which we can actually easily, we got additional containment. So the runtime itself is gonna control the access to all the resources using a capability-based approach, and that should be taken into account when we develop and test our software, because there are additional constraints that are at a runtime level, and all the permission along the chain must match. Otherwise, nothing is going to work. So I mentioned we can run WebAssembly payload, so it's about running an adding an annotation to our container, and this way the container runtime, in this case I'm using Podman, but there are also in the making or already released, even though possibly not stable, way also with containerd to run our WebAssembly payload natively. So it behaves like any other containers, but the payload is just WebAssembly. This is how it looks. You don't need to read all of it. The gist is that what we can do right now, because if you look carefully, we'll see WASI P1, which stands for preview 1. So this is an early warning that things are very much going and very much in flux. So what we can do now is access random numbers, access environment variables, access in read-write files, which is a decent start if we are on the perspective of writing system software. What is an implication of the fact we have access-based control from in the runtime is that while our own application code need no changes, the language runtime could and actually need. There are open issue, or there were open issue a couple of weeks ago against the Go runtime to say, okay, it's not really fully functional yet. So if you take an example, you compile, for example, from Rust into WebAssembly, it works like a charm. If you use the Go official toolchain, you could get in some troubles with the working directory runtime, meaning needs some work from the language runtime perspective. So readers beware. And all of that is not really surprising if, again, we take into account that we are talking about preview 1. So there are limitations in the implementation. They are all the most important limitations. They're actually listed in the Go blog, which explains the addition of 21. The key points is that the WebAssembly run, in general, the WebAssembly runtime, so it's Go translation doesn't really support parallelism, and you don't have a way to export function from WebAssembly to be referenced and called from the Go runtime language. Things are heavily developed, so hopefully those limitations will be obsolete soon, but as November 2023, this is the landscape where we have to deal with. Is any of it a concern? Well, to some extent, but for our purposes of extending our application, it's not a deal breaker yet. So let's see how it looks from the other side. They said we care most. We have a Go server. We want to extend it using WebAssembly because that allows us to have like the plugin experience. Code you compile and load dynamically instead of having to compile it in our application. We are in the middle, the fat middle. So, example application. Again, sorry, going back, if you scan the QR code, you will have a pointed to a GitHub repo, which all the code I have there and more. And there are steps which, for the evolution of the application, which I'm going to talk about, which is the simplest. You have a simple web server, and you want to do all your processing or request processing in WebAssembly. So very simple, very limited. You get HTTP requests, you pass down to WebAssembly, it does whatever it wants given this constraint and gives back a response. So pretty good approximation of plugin. And we are going to use WAS0 because it's the best, I would say, my own personal preference, but also relatively few contenders because this is the pure Go implementation. There are, of course, there are runtimes with Go bindings, but this one is pure Go, so in my opinion is that this has the best look and feel. It's quite nice to work with and with good documentation. So just to make things extremely clear, hopefully, so the host side, which are going to be referenced, is the Go application. And the Go application, as among other modules, includes WAS0. The WAS0 environment has a so-called runtime object, which holds all the compiled module. All of them have two main components: the binary itself loaded as a blob and its working memory. We're going to deep dive in a bit in a second, but those are the main components. So when we are talking about guest, this is our WASM code, which could have been Go, Rust, C, whatever, but now it's the Ghost code running as a guest inside the runtime, bundled in a Go application, which is our host. Unsurprisingly, this is how our main handler is going to look like, what the very oversimplified steps are: create a runtime to, all the structure needed by WAS0 to work, load our module, instantiate it, which is a key concept I'm going to explain in a sec, and then actually run the request. Creating runtime boils down about creating a few objects, handling error, which I'm not in this slide, and instantiating the WASI module, which is create this module, make it ready to run. In this case, the code we don't need to load the code, but we need to make it compile to machine code, which happens transparently, and create the memory for the host to work with, because our compiled code is stateless, but the actual code needs some state to work with, and associating this state is called instantiation, and allocating memory from it, which we're going to use transparently from the guest side, from the WebAssembly code. Loading module, nothing too fancy, is basically a glorified read-all. Instantiation is the process of taking a stateless binary code and binding with resolving, for example, all its functions, which are exported, so you can actually look for them and call them from the host application, from the Go application, and allocating the working memory, which we have memory for each module. And this is also the buffer, basically the shared buffer we can use to interchange data between the host and the guest side. And this is summary, a diagram which represents the working flow. Basically, I'm highlighting, probably, no, it's not, the pointer doesn't work. So in the bottom left corner, you have basically an example of instantiated module with the code, stateless code, bound with the working memory, which only this code in the bluish box could use. So the runtime is the host application, and everything else happens ahead of time. Now, just before we jump to the next, I mentioned processing requests, but there is no explicit, well, actually, when you instantiate a module, whatever is the entry point of a module runs automatically. So what you get is that you can use modules as a very simple plugin mechanism, having the entry point do all the work. For example, we can add all the input from the standard input, bind to the module, let it run, collect the output. It's the simplest model, but it's also, it runs like a side effect, because the entry point is called explicitly, it's called implicitly, and you can add your behavior in there. But the drawback about that is that you have to recreate, you do that as a side effect of instantiation. You cannot call the entry point explicitly. So every time you do that, you must reinstantiate the module, meaning recreate all the, reallocate the memory, resolve all the functions, do all the initialization, let it run by side effect, and then let it go. Now, WebAssembly runtime is quite fast, but if you need to keep state across invocation for whatever reason, will be example at the end, but for whatever reason we need to keep your working memory across invocations, this is lost. So While on one end, we got already a pretty good idea of how we can implement nowadays all the limitation withstanding our own plugins using WebAssembly, it's not perfect because this limitation is a pretty strong one. So what about I want to actually have a good plugin experience, meaning, okay, this plugin is implementing a bunch of functions which I can call as a host application when I see fit. The problem is that there is a limitation of the official runtime. So the proposal to have the Go toolchain, the official Go toolchain from golang.org, exposing functions is on hold. There are a bunch of conversation going, or it was when last time I checked. And the proposal is not implemented yet in Go 121. So your WebAssembly module cannot compile with Go, cannot export functions. So there is nothing to look up and call from our host application. So our previous overly simplified approach to use the module entry point as a way to actually execute code seems the only one. On top of that, a bit of spoiler ahead, passing complex data back and forth from functions is a lot of fun, it turns out, but we're going to see that in a moment. Like now, so you may think, okay, what's the deal about returning a string or pass a string to WebAssembly function? The version implemented right now only gets numerical values as parameter and only one return values. There are proposals at WebAssembly at various stage of implementation to actually have multiple return value, but as it is now, this is an excerpt from the WASM runtime documentation, there is no such support. So how do you do that? Turns out the way to do that is actually to use the memory of the modules and use those binary values, those numerical values as pointers to pass them back and forth from the host application to the guest application. And if all this sounds complex, backwards, error prone, and manual, yeah. At this point in time, it is, again, there are proposals, people are not exactly happy about that, so hopefully this is going to be obsolete very fast. But if you're November 2023, try to do that, the examples are going to say, okay, do like that. Oh, well, okay. But even if we can juggle all of this, we cannot export functions in Go. So how do we actually do that? So one way to do that is using TinyGo. TinyGo, it's a new, different toolchain, independent toolchain for embedded applications. And this is why, for myself, I was happily ignoring about its existence up until a few months ago, because turns out that TinyGo has today, again, November 2023, the best support for WebAssembly in the Go environment. And it actually allows to export functions using TinyGo. If you compile your Go code with TinyGo, you can export functions. Of course, you can use a different language to implement plugins, but we are a GoLab, we like Go. So is that easy? Of course it's not, because TinyGo carries its own set of caveats. Namely, the most striking one is that TinyGo implements limited support for reflection. And the super fun part is that limited support for reflection doesn't mean, hey, okay, my module doesn't compile. Sometimes it compiles just fine and fails at runtime when you actually try to use reflection. And this in turn means that a bunch of modules, including the one in the standard library, doesn't properly work because they use reflection underneath. Glaring example, JSON. On top of that, there is the extra fun caused by interaction between WebAssembly constraints and TinyGo constraints. So we can have concurrency. Concurrency is fine, just one thread, no real parallelism yet. Again, there are proposals in WebAssembly to overcome that, but today, this is the landscape. And we may want to use a non-standard garbage collection for performance. Super fun. If we are not, we didn't give up just yet, and we didn't. Now, this is how a plugin could look like And the entry point is highlighted in red. Now, reminder of we're talking about host and guest because we are going to have a whirlwind tour about the super fun side of using the memory to exchange strings and the liking. So, again, extremely oversimplified version of how the memory looks like. If we are, if there are WebAssembly experts, bear with me. So the memory layout is address space is 32 bits because it could be up to 4 gigs. This is the memory WebAssembly code could use, up to 4 gigs in pages of 64 kilobytes. If you are WebAssembly code compiled from whatever source code, it works brilliantly like we would expect. No surprises, nothing to care about, garbage collector in Go, whatever, works brilliantly. If you have to exchange data, it's not that easy. So this is a key example about implementing a function in WebAssembly, in the guest side, Go, compiling WebAssembly on the guest side, so running as WebAssembly. The key point, I'm gonna skip very fast. No, sorry, too fast. The key point is that you have first to import a function to actually do the heavy lifting from the host side, because what I'm going to do is pass data to that and let it run. And you have to convert the string to base pointer and length. And it's also way worse in the input because at the moment you can return just one value, so you must squeeze the pointer and the length in one value. Luckily, it's 32 bits, so it fits in 64 bits, which is a value WebAssembly supports. Now, let's jump to the DOS side because it's hopefully clear. Now, how does it look like from the, again, reminder of host and guest star because it's easy to get confused. So, on the host side, you need to have call functions from WebAssembly to actually expose expose the function to actually allocate and free the memory, because you may need to do that. You actually need to do that. And this is how it look like when we want to export functions. And let's jump to this. Okay, so very quickly, the output side. So WebAssembly says, okay, this is my string. I'm carving the pointer and the length out of it. Is the highlighted memory. I pass those values back to the host function, which can access the memory using the WAS0 APIs and fetch the data and extract the exfiltrated data. On the other side, if you need from the host side to pass memory, because, for example, you want to implement a string, get string, so get data from the host side, you need to call the memory allocation functions of your WebAssembly module. Allocate memory, copy data in it, and free. Because otherwise you run out of memory, because the memory management is now manual. We are from the host side. When to free it? This is actually a very challenging question to answer, because we don't want to, we need to have this memory have a lifetime long enough so the guest side can fetch it, but we don't want to leak. It's challenging, and possibly the simplest answer is to change the API to overcome these limitations. Because the most streamlined experience will be, okay, I will do anyway in Go, but we have this bunch of limitations. So changing the API is actually something that is worth doing to avoid this pain up until those rough edges are smoothened. So wrapping up this part, TinyGo is needed at this moment to have a good experience on the guest side. Passing complex data is a pain. There are libraries that helps to some extent to avoid the biggest pain, and changing our API to fit it less painfully is possibly a sensible option. References to the documentation from WAS0 about to reduce this pain. Now, armed with all this knowledge, what we can actually do in a cloud, because up until now it was fun and games about, okay, what I can do in server side. So is that, I won't say bad, but is that fun enough for people to, hey, let's just wait a bit more, or are they actually already experimenting with that? They are experimenting with that. Why? Because The cloud infrastructure which makes container run really would benefit from a sandboxed, fast plugin system, because one of the key things is that there is a strong willingness to enable customization, for example, enabling hardware support on the container management system, enabling access to device, making good use of hardware like optimal allocation of CPU is still a hot topic. But at the same time, you don't want to have everything baked in, because, you know, mileage may vary, different people have different expectations or different needs. So there is a strong need for customization, and having a sandboxed, safe as you get environment and fast is a pretty good selling point. The main example I'm gonna talk about is the Kubernetes scheduler. The Kubernetes scheduler is the Kubernetes component which you define your workload, and the job of the scheduler is figure out what's the best node to actually let it run this workload. What's best? It depends, and this is why we very much want it to be customizable. And the definition of best is extremely different. So out-of-the-box experience is a compromise, but I've seen in the wild there are a lot of different options. So the Kubernetes scheduler is the people developing the Kubernetes scheduler are very well aware of these needs. So there is a scheduler plugin framework which is very rich and allows a very extensive list of customization points. Problem is all those extension points are plug-in in the sense that they're strongly self-contained. There is a strong API. You need to implement a few functions. You have a very well-defined way to interact with everything else. But this code needs to be compiled in the scheduler binary. So extending means patching the code, creating a binary, run it. It will be much, much easier for everyone if you can just load your plugin and be done with that. This is the easiest experience. It's not trivial to do, but still the end goal is that. And the scheduler plugin framework wants to have the extension points sharing state with each other. So we cannot just easily do the simple way, okay, I'm running a plugin, I'm leveraging the entry point, running by side effect, and be done. We need the full plugin experience with exporting function to be called from the host application, Kubernetes scheduler in this case. People, since mid this year, are experimenting with that, and this is a project which you can find in the Kubernetes 6 project, which is kind of staging area from code which is under the Kubernetes umbrella, but not ready for prime time just yet. So we have this scheduler extension. Actually, this is a scheduler plugin, but it could load WASM binaries. So all the real decision is deferred to WebAssembly, and you have glue code around that to work with the existing framework. There are lessons about that, and this is the reason I'm bringing up this example, because those are lessons learned and pain actually suffered by people which are trying to do that, because this is a real, existing, well-established application which is trying to extend itself with WebAssembly without, or could not re-architecting itself, because it could be a huge amount of work with all the complication we know about. And one of the complications of that is that the Kubernetes objects are huge, are very big, and we need to pass them across the sandbox boundary so the WebAssembly guest code can use them, change them, or read them. And now we know why this is a big deal. So how we do that in this project? We do that basically marshalling all of them, marshal the big object in a binary representation, much like we will do using for RPC, and passing that. And the guest side does the marshal and reads the fields as needed in a lazy way. This is arguably the simplest and most maintainable option, because the other option will be, okay, let's have code to access each and every field, which goes out of hand very fast. However, this is not for free, because unmarshalling objects create garbage, which is an issue in a severely constrained environment, which is WebAssembly. because the garbage collection implementation, how it works. So the actual suggestion is to use a stronger garbage collection algorithm, but still there is the drawback of that. This is the summary about that. So the other option is to update those objects only when needed. So instead of getting this data frequently, like we will do with the Go plugins inside, they just want to update the data when it actually changes, which is actually a challenging proposition. And this is again an unfortunate reality of having to deal with the current limitations, but this is a preview of how we look like to have an established application running in production and extending WebAssembly at this point in time. And this is also a nice example of how it looks like to change the API to overcome the pain points. And this is the example is that when the scheduler plugin, the scheduler code needs to run an extension point, and this extension point needs to take a decision and say, okay, go, or no, this is not good. They return this called status, unsurprisingly. And this status basically is an error code and the reason for rejection. So if it's successful, does nothing, error code 0 and no reason. But if the object being filtered out or rejected for whatever reason is actually rejected, you get the code and the rejection code. So this is how it looks like with the real code from the Go scheduler extension. For example, so when we get a rejection, we see the error code and the message, but the problem is that this is a complex type. So how do we need to feel the pain to marshal that, save in the memory, return the address encoded as 64 bits to the host environment? Because it's not just that, it's also that we run into all the kind of issue about ownership and memory life cycle. The actual decision the implementers of the WebAssembly extension took, okay, we just return the code and we set error explicitly using a new API. And this is a good example of changing the API to overcome the pain points. What's next for this project? Because the intention is to go with that and having it eventually ready for prime time, as we can gather from the working group upstream. So first of all, they want to implement all the extension point because they started, of course, limited with the most common extension point and growing their way from there. And the other key point is that they are looking to a better event notification mechanism. Why and why is relevant? Because plugins are, extension point in the scheduler, they are triggered when event come. It's an event-based mechanism. So for example, when a workload comes, when a pod comes, the scheduler is evaluated. If the workload could not be scheduled on node, the node could not be picked, it could be hard reject or it could be retry later. And this retry later needs event to be triggered. And at this point in time, again, because of the mismatch between WebAssembly and host environment, it's very limited, and they're looking at ways to make it more efficient. And the open points are the toolchain maturity, and now we have a relatively good idea of why, and also the distribution of the WebAssembly code. Because if we go so far and paid all this price to have actual options to have plugin mechanisms, so load our code dynamically, we need to do that securely. So not just a random person comes, deploys our plugin, and forces it to be loaded. And this, of course, there are options to do that, but no best practice emerged yet. Discussion is ongoing. With that, our very fast tour is done. And now I hope we have an idea of how it looks like in November 2023 to use WebAssembly to extend our Go application. And it boils down to the fact that there are gaps and there are pain points. And this is the glaring highlights, I believe. And with that, I thank you for listening to me, and that's it.
Thank you. Okay, thank you so much, Francesco, for your speech. So right now, if we have some questions, quick questions, because later we're going to have our lunch break, but then Mr. Francesco will be available for other questions throughout the day.
Yeah, folks, if you have questions, just catch me everywhere.
Hi, really interesting talk. You made reference to gRPC earlier and this conversation about shoving binary data on outbound port. Is it possible to use something like protobuf to compile it down to a binary base64 encode and send that out? Could you use that to send complex structs,
Yes.
or is there some gotcha to that?
Yes, thank you for your question, because there is actually a project which I didn't reference, which is about implementing plugins in Go using WebAssembly, and they do exactly like you mean. They, like you said, they do the marshalling using gRPC, using IDL to exchange data between the two sides. So yeah, this is done transparently, and this is actually how this plugin system is implemented.
Okay, we still have some minutes, a few more minutes. Any other question? Oh, yes, sorry.
So I'm sorry if I missed. Did you talk about the component model, WASM component model? Is that a?
No.
Could you say anything about that? Because that seems to be something that might address some of the points that you're talking about.
I cannot comment on that because I wasn't. I didn't look it in a good enough way to comment on that. So
Thanks.
thank you.
How does debugging work with the WASM modules within a Go program?
This is another pain point. And one of the things that people reportedly complain about the WebAssembly experience as a plugin system. So, open question to my understanding. Yeah.
There's actually a WASI debugger from Stealth Rocket.
Yeah, right. The folks which implementing the network. I didn't know. Good. Thank you.
It's been on for a few months. It's quite good.
Oh, awesome. Awesome. Thank you.
One more question to go. Okay, I see we are okay. So thank you again, Francesco. Okay, so we're going to head.
Thank you, folks.
Yeah, sorry.